Hey everyone, here is your intro to related rates as well as the ladder problem. So, related rates compare fixed distances or angles and relate them to the length or to the rates that they're changing. For example, the ladder problem, we're going to deal with a ladder sliding down a wall. So, we'll look at the rate the ladder is sliding down the wall compared to the rate that the ladder is moving against the floor, and how that relates to the angle between the ground and the wall, or the ground and the ladder. And calculus lets us compare the lengths with their rates. Um, so here are some common equations that we'll use, and I can tell you some others. We'll use Pythagorean theorem a lot here. We'll use cone equation, sphere equations for surface area, and usually volume. So for example, like if you have a balloon and you're blowing up a balloon, the rate that you blow in air affects the rate that the radius increases, which just affects the radius itself and the surface area itself and the volume itself. They're all related to each other. The rates are related to each other, hence related rates. So to do that, I'm gonna skip down to these steps at first. So when you solve related rates problems, start by drawing a picture. It'll be helpful. Name the variables, give your items names like variables. T for time. Any rate change is a derivative with respect to t. All of our problems will be lengths changing with respect to time. And make sure you note which quantities will vary and which ones are constant. For example, if you have a ladder sliding down the wall, the length of that ladder will never change, but like the length between the ladder and the floor will change, and the length between the wall and the bottom of the ladder will change. Uh, so number 2, write down the given information and what you're asked to find. Write an equation that relates the variables, so you'll have to use the Pythagorean theorem, area formulas, and then differentiate that formula. Assume that all variables are differentiable functions of t, and then you'll have to use chain rule, product rule, and implicit differentiation when appropriate. And then you'll substitute in your known values and then find what you're looking for, find your unknown value. And then make sure you verify your answer is realistic and specify the units. Make sure you differentiate before you substitute values for any of the variables. And here, we'll practice implicit differentiation with these formulas right up here, these related rates equations. So let's assume that the radius of a sphere is a differentiable function of t, and let v be the volume of that sphere. Find an equation that relates the change of volume with the change of radius, all with respect to time. So this one, we differentiate the volume, which will be dv over dt equals, now 4/3 is a constant, pi is a constant, r cubed is a function with respect to t. So here, we'll leave these constants the same, 4/3 pi, and the derivative of r cubed using the power rule is 3r squared. And implicit differentiation says we multiply by the derivative of r, which is dr dt. And you can simplify that. That's the gist for that one. Now this one, check out b. This is the volume of a cone. Notice it has r and h in this equation, which means you'll have to use the product rule to find the derivative. So this one is dv over dt, that's the derivative of v, equals pi over 3 is a constant, and pull that out. Now you'll use the product rule on r squared and h. So you take r squared times the derivative of h, which is dh dt, the rate the height is changing, plus the second one, which is h, times the derivative of r squared, which is 2r, and implicit differentiation times dr dt. So just as a quick recap, when you solve related rates equations, you'll need to start with some equation like this or this one, differentiate it, and then plug in the values that you know, and you'll be given values. And drawing pictures always helps. So now let's move on down to the ladder problem. And here's a ladder problem. So a ladder is 25 feet long, is leaning against the wall of a house. The base of the ladder is being pulled away from the wall of the house at a rate of 2 feet per second. So let's call this x. Whoa, sorry. Let's call this length x, let's call this length y, and let's call this z. So you know that z is 25. Because that's what we're given, and the length of the ladder isn't going to change even as the ladder slides, but like notice that the length of y will change and the length of x will change. X gets larger and y gets smaller, and they get smaller and larger at different rates. And we're going to find what those rates are. Well, we're going to find the rate of y. That's what we're looking for. So how fast is the top of the ladder moving down the wall when the base of the ladder is 7 feet from the wall? So we're trying to find whatever y is when x is 7. We're trying to find the rate that the ladder is moving down the wall. So we're looking for dy over dt. And if x is 7 and z is 25, you can use Pythagorean theorem to find that y is going to be 24 feet. Okay. What else do we know? We know that the ladder is being pulled away from the wall at a rate of 2 feet per second, which means dx dt is 2. And if we're doing labels, feet per second, okay. So now we need some sort of formula to relate all of these variables, and we have a right triangle and all the side lengths, so let's use Pythagorean theorem. This is x squared plus y squared equals z squared. And then we'll differentiate this, so we get 2x implicit differentiation, they're all functions of t, times dx dt plus 2y times dy dt equals 2z times dz dt. Now we can plug in all of what we know so that we can find what we don't know, which is dy dt. So x is 7, because that's when we're finding when the base of the ladder is 7 feet from the wall, times that rate, dx dt, which is 2, plus 2, y is 24, don't know dy dt, equals 2 times 25 times the rate that the ladder is changing. The ladder isn't changing. It's our constant. So that rate is just 0. So this whole value ends up just being 0. So then we simplify. I'm going to go down here. But I'm not solving b, so just forget about b for now. So this ends up being 28. That's 2 times 7 times 2 plus 48 dy dt equals 0. And you find that dy dt equals negative 28 over 48, which is equal to negative 7 over 12 feet per second. Which just means that the height of the wall, or the height between like the ladder and the ground, is decreasing, that's this negative, at a rate of 7/12 of a foot per second. So it's moving about half of a foot per second down the wall. That's its rate. So I'm going to go ahead and clear this so that I can do b. So this, I called this x, we called this y, we called this z is 25. We're dealing with x is 7 for all these problems, then y was 24. Okay, so dy dt was negative 7 over 12 feet per second. And we know that dx over dt is 2. Alright, so next up, we'll consider the triangle formed by the side of the house, the ladder, and the ground, just like before. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the ground. So we need an area formula for that, which is A equals x times y, base times height. Whoops. Okay, so for part B, we're dealing with area. The area of a triangle is not A equals x times y base times height. It's 1/2 of that. 1/2 of that square, or that rectangle. So now it's the same process. We still differentiate this and then plug in values that we know to find what we don't know. We're trying to find the rate that the area is changing. So when we find the derivative, we're looking for dA dt. And that is equal to 1/2. Now we need to use the product rule for this x and y because they're both functions of t. So x times the derivative of y, just dy dt, plus y times the derivative of x, which is dx dt. All right, now we found dy dt in letter A. We know dx dt, and we know x, and we know y. So we can just plug in all these values to find dA dt. That means dA dt equals 1/2. X is 7. dy dt is -7/12 plus y, which is 24, dx dt, which is 2. And then when you do the algebra and simplify that, you end up with 5/27/24, which is about equal to 21.96 square feet per second. That is the rate that the area is changing for this triangle. So this triangle is getting larger by about 22 square feet per second. Okay, so I'm going to write that down up here, just the answer. 21.96 square feet per second. And let me erase all of this so we can actually do part C. So part C is asking about this angle now, which we haven't talked much about angles in this class yet. But, okay. We're looking for this angle here. Let's call this angle, we've used x, y, and z. Could we call this angle A? So we'll try to find the rate at which the angle of the ladder in the wall, the house, is changing when the base of the ladder is 7 feet from the ground. So, to do that, we can use sine, cosine, or tangent of this angle, and it'll all get us the same thing. So, oops. Alright, sorry everyone, I misspoke. We're trying to find the rate at which the angle of the ladder and the wall of the house is changing, so I picked the wrong angle. So it should be this angle up here. So we'll call this angle A. My bad. So to do that, you can pick any of the trig functions to use. I'm going to pick sine because I like sine. So we know that sine of that angle A is equal to sine of an angle's opposite over the hypotenuse. So this is x over the hypotenuse, which is z, but remember that z is that ladder, so that will never change, so we can just write 25 for that. Now, want to take the derivative. So, remember that the derivative of sine is cosine, so we got cosine of a. Remember that this a is also like a function of t, so then we multiply by the derivative of a, which is dA dt. That's equal to 1 over 25, that's a derivative of x over 25, times the derivative of x, which is dx dt. We know what dx dt is, because that's given to us. It's 2. We don't know what the ADT is. That's what we're trying to find. That's the rate that the angle is changing. Cosine of A. Do we know what cosine of A is? Well, yes, we do. It's relationships of trig. So cosine of this angle is just adjacent, which is 24, over the hypotenuse, which is 25. So this is really 24 over 25 times dA dt equals 1 over 25 times dx dt, which we know is 2. So to solve for dA dt, we multiply by 25 over 24 to both sides. That'll cancel out on the right-hand side. Sorry, the left-hand side. Times 25 over 24. And we get that dA dt equals, let's see, 25 and 25 cancel out. We got a 2 over 24, which is a 1 over 12. So the rate the angle is changing is 1/12 radians per second. So that angle is increasing by 1/12 radians per second. And that is the ladder problem. So email me with any questions you have over related rates or the ladder problem or any other problems that I have posted on here. And have a good week.